Hello, this is our presentation on remote sensing by Eric, Hayden, Stephen, and Amogha. First up, we're going to talk about some of the primary applications of remote sensing, the first of which is weather forecasting. Perhaps one of the biggest uses of remote sensing is being able to predict the weather. Remote sensing enables forecasters to be able to measure wind speeds and atmospheric temperatures so that they're able to forecast the weather over big areas in a quick time span. Also, weather forecasting is critical in being able to identify cyclones, such as the one shown on the left. This is Tropical Storm Jose, which was formed off the coast of Africa. Scientists were able to track and predict the movement of the storm and give residents in the Caribbean over a week's warning using satellites. Another use is to monitor deforestation in the Amazon of South America. Because of how dense the Amazon is, it is nearly impossible to be able to find and stop illegal deforestation by foot. Remote sensing allows enforcement agencies to be able to quickly identify and locate changes in the forest. In the period from 2008 to 2014, the deforestation levels in the Amazon reduced by over 46% after remote sensing measures were put in place. The photo on the left was taken using Landsat satellites, and each pixel represents about the size of a football field. This enables researchers to be able to notice even small fires and clearings. Detecting natural disasters is often a job that remote sensing is responsible for. Remote sensing enables researchers to be able to monitor potential volcanic eruptions, landslides, and floods from a safe distance. On the left is some scans of Greenland, which contributes about 0.5 millimeters to rising sea levels every year. Yearly, some ice sheets lose over 2.5 meters, and those are shown on the left as there are these red areas of loss every year from 2014 to 2018. Some other applications not fully discussed in this presentation include land use mapping and natural resource exploration.
In this section, we will see how remote sensing data is collected and used to predict the Earth's weather. Next slide. The observation of the atmosphere by satellite instrumentation was one of the first uses of remotely sensed data. Satellites provide essential information benefiting the numerical weather prediction or NWP models, which is the future of weather forecasting. Remote sensors collect data by detecting the energy that is reflected from Earth. In remote sensing, the information carrier is electromagnetic radiation, and the output of a remote sensing system is usually an image representing the object being observed. The way the image looks depends on the source of electromagnetic radiation from the object. Sensors on board meteorological satellites are pointing towards ground, enabling them to have a bird's-eye view of the globe from space. These meteorological satellites are typically either geostationary satellites or polar orbiting satellites. Next slide. The very basic application of a meteorological satellite is the identification of clouds. Geosatellites are capable of taking cloud images of the same area continuously 24 hours a day. As it is some 36,000 kilometers from the Earth's surface, it is capable of providing a full coverage of the Earth. Polar orbiting satellites, on the other hand, are low-flying satellites circling the Earth in a nearly north-south orbit at several hundred kilometers above the Earth. As they operate at a distance closer to the Earth, they are only capable of taking cloud images of a limited area of the Earth at each pass. Compared to geostationary satellites, polar orbiting satellites offer fewer and smaller cloud pictures, but the advantage here is that the cloud pictures are of much higher resolution. Different clouds have different characteristics in terms of shape and pattern and have different tones in the visible and infrared images. These differences enable the identification of clouds using a combination of visible and infrared images as seen in the picture below. Next slide.
All right, this is Stephen Boyd. I'm going to be giving some examples of specific remote sensing satellites. Next slide. The first Earth observation imagery was taken by a modified V2 sounding rocket launched from White Sands Missile Range, New Mexico. The V2 rocket was a long-range weapon developed by Germany in World War II. And after the war, the US took over much of the project, which formed the basis for what would eventually become the US space program. Next slide. As always, when we develop a new technology, one of the first things we try to do is figure out how the military can use it. They saw potential in putting cameras on something that could fly very high and go anywhere in the world. So spy satellites became one of the first seriously developed Applications for remote sensing. Corona and Gambit were two competing early designs from the 60s and 70s which flew a limited number of orbits, photographed their targets, and then physically returned the analog film for recovery on the surface. Next slide. 17 KH-11 satellites were launched between 1976 and 2013, with 4 of them still being operational today. This KH-11 is noted for a few features. For one, it was the first remote sensing platform to use digital imaging and real-time data transmission, meaning that no film would have to be physically recovered. For another, its spatial resolution was unprecedented. The 2.4 meter diameter mirror is estimated to have a surface resolution of between 10 and 20 centimeters, in contrast to modern civilian instruments which have resolutions on the order of hundreds of meters. One interesting fact is that the Hubble telescope was very likely a modified version of the KH-11 design. The picture on the left is a KH-11 satellite, while the one on the right is the Hubble. Next slide. On the civilian side, the Landsat program is the longest running Earth observation program, with Landsat 1 being launched in 1972. Landsat 8 is the most recent and most capable. The Landsat satellites fly in polar orbits and mostly monitor visible and infrared wavelengths for resource management and climate study. Next slide. GOES satellites fly in geostationary orbits and provide continuous imagery of the Earth. The program focuses on meteorology applications, but the imagery is also available to the public in real time. Next slide.
I'll be talking about stability and precision. The problem with stability comes from systematic uncertainty that have to be accounted for during calibration phase of the instruments to the ground in order to establish absolute accuracy. The problem further itself when satellite instruments need to adjust itself continuously on orbit. For satellites with remote sensing capability that focuses on taking imagery data requires long-term stability. What is stability? Stability emphasizes on repeatability and reproducibility of some of the characteristic of the instruments with respect to time. This requires stability is some fraction of the change in the characteristic variables. An ideal calibration source is one that is external and roughly always constant in time and able to review from various orbit configuration. Such reference standard can be utilized for correction for drift. Geo Rectification is a process of correcting spatial disorientation in remote sensing data introduced by a platform with sensor. Ideally, satellite retake observation of a given point on the Earth from the same relative location, the same orientation, the same altitude, and ideally the same time of day. Geo Rectification requires accurate knowledge of both position and orientation of the platform that the sensor data was taken from, as well as location reference in the data itself. Next slide. So this one method of finding reflected solar spectral interval is by observing the moon. This is used on the ocean color satellite sea viewing wide field of view sensor, also known as CWIFES. That uses lunar observation to correct for degradation in the linear infrared channel. However, this CWIFE uses lunar data supplied by the ground facility instead of collecting data on orbit. Next slide. Another example of instrument calibration method is an external method called the satellite calibration target. It is a calibration target that is embedded onto the Earth's surface. This embedded market was used to aid satellite camera calibration for spy satellites as part of the 1970 Corona program. The marker is used as a reference to monitor the repeatability and reproducibility, in other words, stability of the instrument as it drifts in space. Next. So this is a summary of our presentation. Next.
In summary, remote sensing is the acquisition of information via sensors without having any physical contact with the object being analyzed. Remote sensing has a variety of applications that impact everyday society. Predicting the weather, protecting our environment, and watching out for natural disasters are a few ways that remote sensing is currently being used.
Remote sensing was one of the first uses of orbital satellites and is one of the most important still used today.
Remote sensors collect data using the energy reflected from the Earth via electromagnetic radiation. Cloud identification is done by analyzing visible and infrared pictures of clouds.
Last but not least, we talked about the stability and precision and its application and how important it is of exploring it in the previous examples. Thank you for listening. That's all for our presentation.